Today, we're jumping into the incredible world of bionic arms. For decades, right, the goal was always to make them more powerful, more responsive. But what if the key wasn't more power, but more intelligence? A brand new discovery is doing exactly that, and it's totally flipping the script on how we think about the future of bionics.
Okay, so let's just get right into it by challenging an idea we all kind of have about technology. I mean, we're always told the next big thing comes from bigger specs, right? More raw power. But when you're trying to decode the signals from the human body itself, is that really the whole story?
For years, this more is better idea was the absolute guiding principle in bionics. And the logic made a lot of sense. A bionic arm has to understand what you want it to do, and it does that by listening to the tiny electrical signals from your muscles. So to get a clearer signal, you must need better, faster, more sensitive hardware. Right?
And for the longest time, the science seemed to back this up completely. Researchers were convinced that to properly recognize the muscle pattern for, say, closing a fist, you had to sample that signal hundreds, even thousands of times a second. The thinking was simple. More data has to mean more accuracy. Or so we thought.
But there was a huge problem with this whole approach of just chasing high-frequency data. The old method, it turns out, had this fundamental blind spot. It was capturing a massive amount of information, yeah, but it was missing something absolutely crucial.
Think of it like this. The old way was like looking at a single, super high-resolution photo of a runner mid-stride. You see incredible detail in that one single instant, but you have no idea if they're just starting their sprint or if they're winding down at the end of a marathon. You're missing the story of the movement. And the consequence of that? Well, without context, the system just gets confused. It leads to what the researchers call spurious decisions. In plain English, that means the bionic arm might misread a signal and make a jerky, wrong move. It's like a translator hearing one single word, but completely missing the entire meaning of the sentence it was in.
So the system didn't just need a signal, it needed the whole story. It needed memory. And that brings us to the hero of our explainer today, a new AI method called Wave LSTM, which was designed to do exactly that.
Wave LSTM just completely rethinks the whole problem. First, instead of just listening to one spot, it looks at how all the muscles are working together, as a team. That's the spatial part. Then, and this is the real game changer, it adds memory. It remembers what the muscles were just doing a moment ago and what they've been doing over the past few seconds. That's the temporal part. So it gets teamwork and it remembers the past.
So here's how it breaks down. First, Wave LSTM figures out the muscle teamwork. Then, it uses short-term memory to notice any sudden changes, what the researchers brilliantly call a memory of surprise. And finally, it uses its long-term memory to track the entire gesture from beginning to end. It's not just seeing one snapshot, it's understanding the entire story of the movement.
Now, all of this sounds great in theory, but come on, does it actually work in the real world? Well, to find out, the researchers set up this fascinating head-to-head showdown. They pitted Wave LSTM against 58 other established methods, using two very, very different pieces of hardware.
Okay, so 22 people wore two different armbands at the same time on the same arm. One was this custom high-spec armband that sampled at a blazing fast 1,000 times per second. The other was a standard, off-the-shelf, low-spec armband, sampling at just 200 times per second. That's a five-fold difference in how much data they were getting. The big question was, how much would the performance crash on the cheaper, simpler hardware?
And the result was just stunning. While all those other 58 methods really struggled on the simpler armband, Wave LSTM's performance barely even budged. It hit 91.65% accuracy on the super high-end hardware and 91.26% on the low-end one. The performance was, for all intents and purposes, identical.
I mean, just let that sink in for a second. It didn't matter if the AI was getting a fire hose of data or just a tiny trickle. Its memory was so powerful that it got the same incredible accuracy with 5 times less information.
And this wasn't just a fluke, The researchers confirmed it statistically. A p-value greater than 0.05 basically means that, scientifically speaking, there was no meaningful performance gap between the two armbands. The smarter algorithm made the difference in hardware almost irrelevant.
The researchers have a term for this, sampling frequency invariance, and it's a total game changer.
It suggests the future of bionics isn't really about more and more expensive hardware. It's about much, much smarter software.
And the real-world implications here are just huge. I mean, think about it. If you don't need those expensive, high-frequency sensors, you can build prosthetics that are so much cheaper. The hardware itself can be way simpler. The devices can use less power, which means much, much longer battery life. And what does all that add up to? It means making this life-changing technology more accessible to way more people all around the world.
And crucially, this was not just some lab experiment on non-amputees. The researchers tested Wave LSTM with 6 transradial amputees, and the results confirmed its power. This approach actually works in real-world situations for the very people who need it the most.
So, this leaves us with a really fascinating final thought. Wave LSTM shows us that by focusing on things like context and memory, a smarter algorithm can totally make up for simpler hardware. It really challenges that fundamental more is better assumption we have about tech, and it suggests that maybe, just maybe, the next great leap forward will be defined by its intelligence, not just its raw power.